All right, so it should be working. Like the audio says it's working. So if it's not working, I don't know what I'm going to do. But okay. So I know you guys sort of kind of went through aromaticity in lecture, like you started on it. So you guys should be able to tell me a little bit about stability. So what's more stable, conjugated systems or aromatic systems? Aromatic. Aromatic is way, way better than conjugated. And so that being said, benzene is a lot more stable than what it's expected to be. So the stability is much higher. And cyclohexatriene is just like the IUPAC name for benzene. So that's all that is. So what it's just trying to say is like, when we look at a triene, right, we expect it to be at a certain stability, right? But it's not just conjugated, it's also aromatic. So the stability for the aromatic system is a lot higher than what we expect it to be. Exactly. So it's kind of saying, like Dr. West showed you this graph in lecture, and it's like predicted stability or whatever, and then it shows like the predicted stability of benzene, and it's like the actual stability of benzene. And I don't know if he's done that yet, but yeah, it's just saying like theoretically it should be here, but it's all the way up here. So why is that? And that's because it's aromatic. If that didn't make sense, let me know and I can re-say that, but I think it was okay. So when we're talking about aromaticity, we have like 3 rankings. So you can either be aromatic, you can be non-aromatic, or you can be anti-aromatic. So aromatic is the best. What do we think is in the middle? Non-aromatic. I'm just going to say non-A. And then the crappy one is what? Anti. Cool. So anti-aromatic sucks. We want to do anything we can to avoid being anti, because anti is awful. And we'll talk about why exactly it's awful in a little bit. But anything that's non-aromatic is pretty much like anything hanging out, right? Like it's whatever, it's in the middle. It's kind of like isolated, right? Isolated was, but then aromatic is super good. Okay, so the criteria to be aromatic, there's 4 things. Did you guys cover that in lecture at all? You did? Okay, so what are they? Cyclic, planar, fully conjugated. Yes, okay, so let's talk about all of these. And does anyone know what the 4n+2 rule like is called? Huckel's rule, yeah. Or maybe it's pronounced differently, I don't know. Okay, so cyclic literally just means it has to be a ring. That's pretty straightforward. Planar is what tends to confuse people, so I'm just going to say for rings less than 8 members, assume it's planar. So if it's a ring that's smaller than this guy, assume it's planar. If it's 8 or more members, then we're going to talk about when it's planar versus when it's not. But if it's less than this, assume that it's planar. Dude, sure. Okay. So what we mean by fully conjugated is what we talked about last chapter. We want it to be fully sp2. So no sp3. And as a reminder, what did we talk about last chapter when we talked about sp2? Bro, please. What can be sp2 besides double bonds? Cations, anions, and what was the last one? Radicals. Yes, double bonds, of course. Cations, anions, radicals. So all of those things can be sp2. Heteroatoms atoms can be sp2 or sp3, but we're going to talk about that. All right. Any questions on what those rules mean or anything like that so far? We're going to talk about that in 1 second. I just want to make sure the first three are good. So the reason the first three are really important is because we have the same first three rules for anti-aromatic as well. So it has to be cyclic, planar, fully conjugated. So then the big difference between aromatic and anti-aromatic is just the number of pi electrons. So for aromaticity, you guys told me Huckel's rule is 4n plus 2. And for anti-aromatic, it's 4n. So a lot of people tend to get confused at this point because they're like, okay, well, what does n stand for? What number do we substitute for n? Things like that. I like to tell you guys, just ignore that whole thing. Like, n is just any real number. And for any ring, you can have any number for n. So all it's saying is that in order to be aromatic, you have to have some multiple of 4n plus 2, which means 2, 6, 10, 14, etc. Any multiple of 4 plus 2. So 4 times a number plus 2. Versus to be anti-aromatic, you have to be some multiple of 4. So 4, 8, 12, 16, etc. And we're going to talk about like what exactly that number means, how do we count electrons, things like that. But so far, in general, do those rules make sense? Okay, cool. How do we feel about like cheap way of doing the electron? Is that okay? Do we like those numbers? Okay. So non-aromatic or not aromatic, that's easy because it's breaking any of these rules. So if it breaks any of these rules, it's non-aromatic. And so what could that look like? Well, if we have any sp3 atoms, it breaks the conjugated rule. If it's non-planar, it breaks the planar rule. If we have an odd number of radicals, that means we're going to have an odd number of electrons, right? So that's going to break both the 4n plus 2 and the 4n rule. And we're going to talk about a couple other instances, but those are the main ones I want you to know for right now. How do we feel? Okay, cool. I'll leave that up for another second, and then molecular orbital theory, we're going to skip for right now, and we're going to come back to it after we've done the examples. I don't know why I have it like this in the handout, but I guess it'd be like that. So the first one we're going to do is this lovely little triangle right here. So what do we think? Is this cyclic? Yes. Is it smaller than 8 members? Yes. So we're going to assume it's planar. Is it fully conjugated? No, exactly. So what is this guy? sp3, exactly. So like Eric said, it's going to be non-aromatic. All right, so compare this one to this next one. It's also cyclic, it's also planar. Is it now fully conjugated? Yes, it is, because we have a cation. Cool. So how do we count the electrons? We're just going to draw our lovely orbitals, right? And we have a plus charge here, so that means that orbital is empty. And then we know that the double bond is going to have 1 electron in each orbital. So how many pi electrons do we have total? 2. All right, so 2 pi electrons, is that 4n plus 2 or is it 4n? 4n plus 2, so this is aromatic. Cool. Any questions how I did those two, why they're different? So if we had 4n plus 2 and we substituted 0 for n, it would be 4 times 0 plus 2 equals 2. It's just going to be 0. Yeah, that's the thing. That's why I say don't remember it as 4n plus 2 necessarily, because you just like, yeah, it just could be any. Like it could be any n. It doesn't matter. Does that make sense? Because usually if they give you something like this, like you have to know, oh, it's 1 double bond, so you have a specific n, right? But that's not, the logic doesn't work that way, unfortunately. All right, so let's do the third one. Now we also have cyclic planar, and it is fully conjugated because it's an anion. But how many electrons are going to be in that p orbital? Oh, it's going to be 2. No, my bad. In that one orbital, that one negative p orbital, there's going to be 2. But yes, total, then it would be 4. You guys are correct. So cations have 0 electrons in the orbital. Anions have 2. Radicals have just 1. And I can repeat that if anyone needs. So cations are going to have 0 electrons in the p orbital. Radicals have 1 electron in the p orbital. And anions have 2 electrons in the p orbital. Okay, so overall we have 4 pi electrons. So is that aromatic or is that anti-aromatic? Anti. So I'm going to write that as AA. And what's this? Okay. So do we have any questions on this, like, simple one so far? All right, so we're going to get into some heteroatom rules. What happened? Ah, yes. Yes. Okay. So the heteroatom rules, I'm going to go through them one at a time, and we're going to do an example. So hopefully that'll make it make more sense. So the first rule is if we have single bonded heteroatoms, not necessarily. So if they're single bonded, it can actually choose between sp2 and sp3. Forgotten it. And it's either going to donate 0 or 2 electrons. Write that in the next line. So this is super important. If it's sp3, it will donate 0 electrons. It can't donate any electrons. But if it's sp2, it has to donate no more and no less than 2 electrons. So it's going to donate 1 lone pair. And I'll leave this up for a second if anyone's still writing it down, and then we can do an example. Also, while we're here, what counts as a heteroatom? Oxygen, nitrogen, sulfur, anything that's not carbon or hydrogen. Awesome. All right. Whenever you guys are ready, let me know. Okay. So we go up here, and then I'm just gonna go back to like the first row, and then we'll kind of skip around. So we see this oxygen right here. I see a single bonded heteroatom. There's two things I'm gonna do. One, I'm gonna make sure he's not tricking me with the number of electrons he has drawn, right? So oxygen has two lone pairs, but I told you the absolute maximum number of electrons you can donate is how many? Two. So he's doing that to trick you. So first thing you do is cross out one of the lone pairs because it cannot donate more than two electrons. So more than one lone pair, that's a trick. Next thing I'm going to do is I'm going to write down sp2 and I'm going to write down sp3. And we're going to figure out which one of those would be more stable. So if we're sp3, that automatically means it's what category? Non-aromatic. Okay, so anytime we see any sp3, it has to be non-aromatic because that breaks the fully conjugated rule. All right, but let's say it's sp2, right? If it's sp2, it has to donate how many electrons? 2. So that would make the total electron count for this what? 4. All right. So 4 pi electrons. That would be what? Aromatic or anti? Anti. So we're stuck between non-aromatic and anti-aromatic. What's more stable? Non-aromatic. So in this case, non-aromatic would be more stable than anti. So this oxygen is going to be sp3. And this molecule is going to be non-aromatic. And that's what we mean by like it could choose sp2 or sp3. In this case, the most stable option is sp3. And we donate how many electrons? 0. Cool. So if it's sp3, it's going to donate 0. That's a kind of tricky question he might ask sometimes. Yes. Yeah. Okay, so basically, when we have a heteroatom, it's a little bit more flexible in the carbons. And what I mean by that is the orbitals are more flexible. So like, if this makes no sense to you, just drown it out. You don't have to know it for the exam. But like oxygen has 2 orbitals where it puts its lone pairs, right? So we could either bend both of those on a different plane, or we could put one of them as a p orbital to match the other electron and keep the other one flat. So I'll draw it in like 3D-ish for you. So if we have this, our oxygen could either look like that, and it'll have 2 electrons here, and it'll have another orbital like this, where it has its other lone pair. And in this case, it would be sp2, because it's using those 2 electrons to be on the same plane as the double bond. Or we could just bend it down this way so it's not in the plane. So that one orbital is flexible. It could either point away from the double bond plane, or we can move it so it's pointing in the same direction. And that's why it could be sp2 or sp3. So don't think of it in like terms of bonds and like how many lone pairs and how many bonds it has, because heteroatoms don't always work that way. Yes. Great question. So let's do this one. Right? How many lone pairs does nitrogen have if it has 3 bonds? 1. So in this case, he didn't draw the lone pair to trick you. So this nitrogen could either be sp2 or it could be sp3. And if it's sp3, it always has to be what? Not anti. Non-aromatic, yes. Because it breaks what rule? The rules, yeah, but it's going to break the fully conjugated rule. Because to be fully conjugated, you have to be completely sp2. All right, so in this case, if it is sp2, how many electrons does it donate? Okay, so yes, the nitrogen specifically donates 2, but overall we get 6. And so which rule does that follow? Aromatic or anti? Yes, so this time it's going to be aromatic if it's sp2. So it's not always going to be anti-aromatic if it's sp2. It'll depend on the size of the molecule. So in this case, what's more stable, sp2 or sp3? sp2. So this time, the nitrogen will choose to be sp2, which will make this aromatic. And just so you know, it donates 2 electrons. Great question. So instead of drawing out the orbitals every time, what I suggest doing is each double bond is worth 2 electrons. So I think 2, 4, and then assuming it's N is sp2, we count 6. Yeah, they are. Wait. One more time. It is. So, okay. The lone pair is on the nitrogen. So the way the bonds are going to be set up, it'll be just like this. Except now, it'll look like that. So we have 1, 2, and it's not an oxygen. That's my bad. Nitrogen. Okay. So each of the carbons has a double bond. So they're going to have 1 electron in the p orbitals. And another way we can write double bonds is by drawing them like this. I don't know if you've ever seen that in lecture. You have? Yes. Okay, cool. So all it means is that it's a double bond. And then the nitrogen, if it's sp2, it'll do this. And it'll have 2 electrons in that p orbital. So if it wanted to be sp3, it would just get rid of that. And on a different plane, it would do this. Yeah, so the total p electrons, exactly. So the reason, if it was up like that, it would count, not because it's on the carbon, but because this forms like a pi system, which is not something you super go into, but all these electrons are basically delocalized. And what that means is like you could do resonance all across the ring. He does use the term delocalized, so just know it just means resonance throughout the whole ring. I know this stuff can be hard to get if you like can't see it in 3D. So do we feel okay-ish? Yes. Okay. So yes, all right. we have a little asterisk in this rule. So single bonded heteroatoms are going to do what we just said, except in the case of boron. So boron, aka B, that's an exception to the rule. And the reason it's an exception is because boron is always sp2, but it has 0 lone pairs. So it's always sp2 and donates 0 electrons. And then we'll see what exactly that means in a second. Okay, so if we go up here, I'll put this oxygen one on the side as like a reference, I guess. So boron, we said, is always sp2, but it donates 0 electrons. So how many pi electrons does this system have? 2, because it only has the electrons from the double bond. So if it has 2 pi electrons, and can we say that it's cyclic, planar, and fully conjugated? Yes. Okay. So would that be aromatic or anti-aromatic? Aromatic. Cool. So boron can almost be used like a cation, because just like a carbocation, it's going to be sp2, and it's going to have 0 electrons. So the reason I point that out is on your exam, if you see like 2 answer choices, you have boron, and then you also have like the same molecule but a cation. You don't have to spend the time doing both of those because you know the same. That's it. Exactly. So it doesn't have any lone pairs. Another example of that would be this one right here. So we know that boron has to be sp2, but it gives you 0 lone pairs. So how many electrons do we have in this system? 4, exactly, because we're only counting the double bonds. That's 4 pi electrons, and that would be anti-aromatic. Cool. So is the boron rule okay? Okay, cool. So I'll show you all of these so far in case anyone forgot to write anything down. And then we're gonna move on to the second heteroatom rule, which is like 2-parter. So, all right. So we talked about if heteroatoms are single bonded, but what happens if they're double bonded? So if a heteroatom is double bonded, it must be sp2. So if it's double bonded, it has to be sp2. Actually, before you write that down, I'm so sorry. I'm going to break it down into 2 parts. I forgot. I said it, but then I forgot. So if it's double bonded and it's double bonded inside the ring, it must be sp2, and it donates 1 single electron. And if it's, I'm going to move up a tab. If it's outside the ring, it must be sp2 and donates, wow, that's a really ugly T. It donates 0 electrons. So we're going to talk about the difference, like what does it mean inside the ring versus outside the ring. But the general rule here is if something, or not something, if a heteroatom is double bonded inside a ring, it has to be sp2, and it donates one single electron, not a pair, but just one single electron. And if it's double bonded outside of the ring, it has to be sp2 again, but it's going to donate 0 electrons. Do this up for one more second, and then we'll do a couple examples. I can't tell if I'm talking really fast or really slow today. Thanks. Okay, we're going to go up. So let's do this one first. So what do we think? Is this double bonded inside or outside of the ring? Outside, cool. So if we have a double bond that's like a ketone or something, that's what we consider outside the ring. So this carbon right here is sp2, and it has 0 electrons to give. So this is almost like what again? Yeah, it's almost just like a carbocation. So sometimes what I'll do is I'll just cross this out and I'll put a plus, just so it's a little bit less daunting. Plus, again, if they give you both of these answer choices, you know it's going to be exactly the same, because how many electrons do we have? 2. And 2 electrons follows which rule? 4n plus 2, which is Huckel's rule, which is aromatic. Cool. Any questions on? Yes, okay. So I just, the only reason I crossed it out is because it's easier to see for me, but essentially it's going to be the same thing as a carbocation because it's sp2 and it has 0 electrons. So yeah. It wouldn't be positive, but it would be empty. So the way I want you to think about it is resonance is always going to pull these electrons to the oxygen. So the electrons are never going to donate into this system. It's just going to donate towards the oxygen. So it has a delta plus, but not like a positive. That girl was like, I'm here for calculus. That's not calculus. Okay. So this example is this inside or outside of the ring? Inside, cool. So if it's double bonded inside the ring, we're going to get rid of this lone pair. Because that lone pair is on a different plane. It cannot interact whatsoever. It's only here to trick you. And the reason for that is, functionally, this nitrogen is exactly like a carbon. Because since it's part of the double bond, its p orbital is locked in that double bond, and it only has one single electron in it. So it must be sp2 and donate 1 electron. And so how many electrons does this guy have? 4, yes. And so which rule does that follow? What was that? The 4n, which is anti, yes. And then I'll draw like the lone pair just so you can see it like on a different plane. No, in this case it cannot because it's stuck in a double bond. That's how they get you. Yep. So when it's double bonded inside the ring, it's essentially just like having a carbon there. And he'll give you one that I didn't include here for some reason. It looks just like benzene, except there's a nitrogen here. And again, since that is functionally exactly like a carbon, this guy is still going to be aromatic because there's 1, 2, 3, 4, 5, 6 pi electrons. Questions? Yes. Yeah, okay, so basically, those are radicals, and they're kind of ugly because the program I used was just kind of ugly. So let's say we have this guy, right? Is he cyclic? Is he planar? Yeah, we can assume so. Is it fully conjugated? Yes. So the reason it is because radicals are sp2. And let's count the electrons, right? So how many electrons do we have total? 6. So we have 6 pi electrons. So it is aromatic. Cool. If this had 1 radical and 1 carbocation, it would be what then? It'll have 5, so it'll be what? It'd be non, exactly. So if you ever see something like this and it has 1 radical, such as this example right here, you don't even have to do anything. 1 radical or an odd number of radicals immediately tells you non-aromatic. Because we know there's an odd number of electrons. Questions? All right, so we are going to have to talk a little bit more about this on Monday, because we are pretty much out of time. But any questions, comments? How do we feel? Yes. Great question. So let me stop sharing. Actually, yeah, let me stop sharing for 1 second and then. No. Dr. West, please. Nope, I don't want Case Western. Still broke. Yes. Yes, exactly. Okay, so I'm sharing this screen with you now. Screen, start. Okay, so in chapter 11 and 12, so Dr. West says reactions of alcohols, dehydrations, protecting groups, but he already tested you on those 3 things. So maybe you'll have like 1 question from that, but I will put it in like the review summary. Did I give you a cheat sheet for exam 1? Nope. Oh, wow, that's mean of me. So I'll do one for exam 2. And it'll be kind of like a summary page of like what you have to know. But please don't let that be your only source of studying, because people get very mad when they don't get 100. Yeah, I think there'll maybe be like 5 total, if that. Like for 11 and 12, it'll be like 5 total questions, I think. Yeah. So then 13 is kind of long, but don't let this list like freak you out. So it is a lot of easy stuff. So conjugated compounds, when it talks about naming, that's not naming dienes and stuff. We talked about that. And then when we talked about stability and resonance, that was all about configuration and conformation. Molecular orbital theory, we talked about that. Yes, what's up? What is this? I will show it to you guys tonight. It's just like a little thing. It has like absorption and whatever. All you really need to know is that epsilon equals molecular absorptivity. Something like that. I will show it to you later. You don't have to actually know the law. You just have to know like what each thing stands for. And then yeah, 1, 2, 1, 4, and then deals all the reactions. When it says stereospecificity and retrosynthesis, so stereospecificity just means like endo and exo product. So just know that. And then characteristics of deals all the reaction. I don't know why that's its own point. That's just everything we talked about. And then the UV spectrum, plotting absorbance, whatever. You just have to know generally what UV spec is. And then for chapter 14, aromatic compounds. So just know aromaticity. I don't know why there's a billion freaking like points. You just have to know aromaticity. You have to know naming aromatic compounds, and we didn't have time to go over that today, so I'm going to send you a little like practice sheet, and you guys have to know the IUPAC name, and you have to know the common names. Common names are super important. I'm going to give them to you, but it's just things like, okay, methyl with a benzene. Benzene with a methyl on it. What is the common name? Close, toluene, exactly. And then when we have benzene with an NH2 on it. Aniline, exactly. So there's just a couple of those that you have to know. But again, I'll send you that little worksheet so you know. I don't think we're allowed to share it with you, but we are also going to go over it in the exam review tonight. And I will, basically what I'm going to do is I'm going to go through this and I'm going to make it like easy to and not like super overwhelming. And then I'll send you a version of it, but I can't forward this one to you because Dr. Weston. No. We'll see. I haven't made one yet, but I'm going to see if I have one from last semester available. If not, I'm just going to use the cheat sheet that I made and then just add to it, and I'll send that to you guys after. Okay, and then chapter 15. There's all this stuff for 15, but Dr. West said this is where he plans to cut it off. So it's really not too bad. It looks like there's a lot of stuff on it, but we will talk about that. This will be like maybe 25 minutes in SI on Monday. But yeah, don't be too freaked out. It's not too awful, I promise. We will get through it. Leaving you guys. I will see you guys later, and if I don't, happy Friday. Have a good weekend. I missed you so much. Heart, heart.